Have you ever wondered if the mere act of observing something could change the course of events? Welcome to the fascinating realm of quantum physics, where the seemingly impossible becomes possible. Today, we're plunging headfirst into the enigmatic world of the observer effect. Now, what is this observer effect we speak of? It's an intriguing concept that suggests the very act of observing or measuring a quantum system can alter its outcome. Yes, you heard it right. It's like saying, by simply watching a football game, you could influence whether the ball goes into the net or not. Sounds mind-boggling, doesn't it? This brings us to a phenomenon that is at the heart of quantum physics, the wave-particle duality. This is the idea that all particles can exhibit properties of not only particles but also waves. It's as if you're eating your cake and still having it. In the quantum world, a particle like an electron can exist in multiple places at once, like a wave. But the moment we try to observe it, it behaves like a regular particle again, existing in one place. So how does this tie into the observer effect? Well, the very act of observing or measuring forces the particle to choose a state. It's as if the electron says, "All right, you got me, I'm not a wave, I'm a particle." But the question remains, why does this happen? Why does the act of observation influence the state of the particle? This is the quantum riddle that has puzzled scientists for decades. The observer effect is a testament to the peculiar nature of the quantum world, where our conventional understanding of reality is continually challenged. It's a world where the act of observation intertwines with the observed, creating a complex dance of cause and effect. So, the question remains, can our mere observation truly influence the reality around us? Well, stick around as we unravel this quantum puzzle in the upcoming scenes. Until then, keep wondering, keep questioning, because that's what keeps the world of science turning. Scene script. Sounds complex, right? But let's break it down to its simplest form. Imagine you're at a party, and you've got this incredible ability to be in two places at once. You're both tearing up the dance floor and refilling your punch cup in the kitchen. This is a bit like the concept of superposition in quantum physics, where particles can exist in multiple states at the same time. But the moment someone at the party notices you, poof, you're only in one place. You're either grooving to the music or quenching your thirst in the kitchen, but not both. This is akin to the observer effect, which suggests that the act of observing or measuring a particle affects its state. Now let's bring in the famous double-slit experiment as an example. Imagine firing tiny particles, like photons or electrons, through two slits onto a screen. Without anyone watching, these particles behave like waves, creating an interference pattern on the screen. It's like they go through both slits at once, but the moment we decide to observe which slit the particle goes through, it behaves like a particle, not a wave, and the interference pattern disappears. It's as if these particles know they're being watched and decide to behave differently. A bit eerie, isn't it? This phenomenon is what scientists call the collapse of the wave function. When we observe or measure, the superposition collapses into a single state. So, what the observer effect tells us is that the mere act of observation influences the observed. It's like our act of looking forces the universe to make a decision. Just as you can't be doing the robot dance and sipping punch in the kitchen at the same time once someone spotted you at the party, particles can't be in multiple states once they've been observed. In essence, until we decide to look, particles exist in multiple states simultaneously. Now, let's dive into the heart of the observer effect, the Heisenberg uncertainty principle. The Heisenberg uncertainty principle is like the celebrity of the quantum world, making headlines for nearly a century. This principle, proposed by Werner Heisenberg, a German physicist in the roaring 20s, is a cornerstone of quantum mechanics. At its core, the Heisenberg uncertainty principle states that it is impossible to simultaneously know the exact position and momentum of a particle. That's right, impossible. Not just difficult or challenging, but downright impossible. It's like trying to catch a greased pig at a county fair. The more you try to pin it down, the more it slips away. Now, it's important to remember that the Heisenberg uncertainty principle isn't about our technological limitations or our inability to make accurate measurements. It's not a statement about what we can measure, but rather about what nature allows to be measured. It's a fundamental property of the quantum world, a world that doesn't play by our usual rules. So, what does this have to do with the observer effect? Well, remember that the observer effect tells us that the act of measuring something can change the thing being measured. The Heisenberg uncertainty principle takes this a step further. It tells us that the mere act of trying to measure the position of a particle makes its momentum uncertain, and vice versa. In other words, the more precisely we try to pin down one property, the more the other property starts to blur. It's like trying to watch a movie and read a book at the same time. The more you focus on one, the more the other slips away. This is the heart of the observer effect, the idea that by merely observing, we are interfering, and it all stems from the Heisenberg uncertainty principle, a principle that reminds us that the universe isn't just strange, it's quantum strange. So the more precisely we try to measure one property, the less precisely we can know the other. So, what does this all mean for us and our understanding of the universe? Well, the observer effect in quantum physics is a bit of a conundrum. It's like a cosmic prank, challenging our classical understanding of reality. You see, we've grown up in a world where things exist independently of us. A tree is a tree, whether or not we're there to see it. But the observer effect suggests otherwise, that the very act of observation affects the observed. It's a bit like the universe is saying, "Gotcha!" This has profound philosophical implications. It forces us to reconsider the nature of reality itself. Are things out there independent and self-contained, or are they in some way dependent on us, the observers? It's a question that has puzzled philosophers and physicists alike, and let's be honest, it's a bit of a mind-bender. But it's not just about philosophical musings. The observer effect could have practical implications too, particularly in the fields of quantum computing and encryption. Quantum computers, for instance, could potentially harness the weirdness of the quantum world, including the observer effect, to perform computations at speeds unimaginable with classical computers. They could solve problems in seconds that would take classical computers millions of years. As for encryption, quantum mechanics could make communications virtually unbreakable. You see, if someone tries to eavesdrop on a quantum encrypted message, they would inevitably disturb the system, revealing their snooping. It's a bit like a self-setting burglar alarm. So, as strange as it may seem, this quirky feature of the quantum world could have real-world implications. It could revolutionize computing, make our communications more secure, and force us to rethink our understanding of reality. It seems like the observer effect not only changes the world of particles, but could also change the world as we know it. Let's wrap up what we've learned about the observer effect. We've journeyed through the mysterious world of quantum physics and peeked into the strange concept of the observer effect. Like Alice through the looking glass, we've seen that observing isn't just a passive act in the quantum world, but a game changer. We've learned that particles can exist in multiple states at once, in what's known as a superposition. It's like Schrödinger's cat being both alive and dead, until someone peeks inside the box. That's wave-particle duality for you, the heart of the observer effect. This quirky quantum behavior tells us that the mere act of observation can determine whether a particle behaves like a particle or a wave. Then, we wrestled with Heisenberg's uncertainty principle. Remember the pesky problem of trying to measure both the position and momentum of a particle at the same time. As we found out, the more precisely you try to measure one, the less precisely you can know the other. That's Heisenberg's uncertainty principle in action. We also pondered the profound implications of these ideas. The observer effect and the uncertainty principle don't just apply to tiny particles, but to the universe at large. They challenge our understanding of reality itself and remind us that our role as observers is far from insignificant. So, there you have it, the observer effect in a nutshell. We've delved into the quantum realm, wrestled with uncertainty, and explored the profound implications of these ideas. We've seen that the universe isn't just a static stage where events unfold, but a dynamic player that changes with observation. So, next time you're observing something, remember, you might just be changing the outcome.